So I'd like to do a couple examples around convolution, and particularly around discrete convolution, because I know that this is an important topic and to want to kind of think about some of the aspects. Now we're going to look at convolution with this sort of an input, and this sort of input that goes between this x of n, which is 0 to 6. And what's really cool about it is that it kind of has this almost shape as a sine wave, although it might be a triangle wave depending on what you're looking at. And again, convolution will typically be an input times an impulse response. An impulse response is if I put an impulse into the input, this is actually what I get for my output. And so any actual output is the combination of each of those times an actual input that are actually put through. Okay, great. So what am I looking at here? Well, the first one I'm looking at is something that's going to be two that are both 1. So you might imagine this looks like a boxcar kind of filter of size 2. Just to kind of see what it looks like. It is of width 2. I'm going to have another one which is going to be a derivative kind of function. So it's a 1 and minus 1. And kind of see what it does. And then I'm going to have another one that's just going to be 1, 2, and 3. This is now of width 3. And why pick this? Well, why not? It just seems like an interesting one to pick. So what do we see when we do this? Well, when we take the averaging structure, what we notice is that we get something that looks almost sinusoidal. And in fact, you might imagine that what we've done is we've actually eliminated some of the hard edges, smoothed it out, and we're getting sort of the primary sinusoid out of this. Something to note here is that this length is of length 7, this was of length 6. And this is length 2. And so this seems to fit exactly what you'd expect for the convolutional pattern, which says, all right, so the output width for a discrete size is going to be the size of the input plus the size of the impulse response minus 1 for an FIR system. For an IR system, well, it goes infinitely long, so you have an answer. If you look at it, you get a similar sort of length here on this 2 case. But what's interesting in this particular case is that you definitely see the changes come out, right? So you see in the input the 2 upward going changes, and that gives you a half, and you see 4 downward going changes, and then you see 2 upward going changes. And that's exactly what comes out of this response. And again, its length also sort of conforms as you would expect. So it's cool, and you see it goes from 0.5 to minus 0.5, which is exactly what you'd expect in terms of the changes. Now in the third one, what you end up seeing is this increasing case. Notice that the amplitude here goes up to 4. You see immediately this sort of rise as you get various inputs. It's actually a rise going a bit faster. And then you see these sort of interesting pieces as you work down. Notice it goes 1 longer than the other 2 because actually it's 3 rather than 2. So what you see with all of this is that you get a number of different interesting cases with convolution, particularly discrete convolution. And even when you talk about doing continuous convolution, having the discrete side kind of helps give you intuition of what you're really seeing. And so this can be a really, really strong advantage for you.